Hello everyone, I'm Akif and we're having our third lecture on artificial intelligence. This lecture is about inference in first order logic. In the previous video we discussed about first order logic and we did represent them in the form of first order logic, I mean the sentences. And we discussed in detail about one variable sentence or two variable sentence, and here by variable I mean the subjects. Now let's move forward. So if you have a first order logic, it's also known as predicate logic. The reason is because a predicate is what forms the skeleton. Let's have a look at this example where we have to represent Socrates is a man. Then Socrates will be inside the parentheses and outside this is man. So man is the predicate and Socrates is the subject. Similarly, if we have to represent a two variable predicate, then we'll represent it like this. X is Y's brother, so it will be represented like this. X is Y's brother. Okay, now X loves Y. X loves Y. Now if we have a statement which goes like, if X is the brother of Y, then X loves Y. That will represent like this. If X is the brother of Y, then X loves Y. Now if someone comes and says that everyone loves his or her brother, this is how we will represent that. Let me rub this. Everyone loves his or her brother. So we are going to represent it like this. Okay. And the reason why we are going to have universal quantifier here, which is X and Y, is because everyone means every person, which will be represented this by this X variable, loves all of his or her brothers. So Y represents the brothers. So this can also be represented in this form. One universal quantifier X comma Y. X is the brother of Y, then it's for sure that X loves Y. So this can be substituted instead of two universal quantifier. So this and this both are one and the same thing. Now let's have a look at another example. So far what we saw is that inside this representation, for example, we had Socrates is a man. We saw a single literal or single entity inside this, or a single variable inside this, but at times we could have a complete predicate inside this. For example, if we have to represent mother of X, we can also represent it like this. So this also means mother of X. Okay, now if we have to represent everyone loves his or her mother. Okay, in the previous case we saw, for example, X loves Y. Now here we are talking about X loving his mother. So we know for everyone we will have a universal quantifier, which is X. Okay, so X loves his mother, and we know that we are going to represent mother with this kind of representation. So it will be like this. X loves his mother. So this is another way to represent it. Instead of a literal, we are going to have a predicate, and inside that predicate we are going to have the subject. Similarly, if we have to represent Jonathan loves his mother, we will represent it like this. Jonathan loves his mother. Okay. And this is how we would represent everyone loves his or her mother. We discussed it. Now, let's revise and try to recall what we learned in the previous lecture. For example, some dogs bark. Now, some, here the sum will be represented with an existential quantifier. Then we are going to have a separate representation for dogs, for separate representation for bark. So let's try to solve this. If X is a dog and X barks, but it's talking about sum, so we are going to have existential quantifier here. And we know that when we are talking about existential quantifier, then we will have AND operator. So this will be represented like this. For some X, if X is a dog and X barks, that's how we represent this. Okay, this is this. Now all dogs have tails. So for all, we're going to have a universal quantifier. Then we will represent dog and we will represent tails. So let's try to solve this here. First, we know that we're going to have a universal quantifier. Then let's represent X as a dog with this. X has tail. And we know when we have a universal quantifier, then it's going to have implication along with this. So let's try to represent it. That's for all X. If X is a dog, then it's for sure that it has a tail. Okay, so this is how we represent this. Now sometimes we can use constant also in the representation, so we'll discuss this. So all dogs have 4 legs. It could be represented like this. For example, here, all dogs have 4 legs. I can represent it like this. So we know all is here. We are going to have a universal quantifier. Then we are going to have another thing, which is to represent dog, and then we have to represent this has 4 legs. So if X is a dog, we'll represent it like this. X has 4 legs, we'll represent it like this, has 4 underscore legs, or you can represent it in whatever way you want. Now we know with universal quantifier there's an implication, so let's try to represent this. For all X, X is a dog, therefore X has 4 legs, has underscore 4 underscore legs X. So this is how we represent this. But sometimes we can have another representation. Instead we can have constant inside this. We can represent 4 legs with the help of a constant. We'll represent 4 legs with the help of constant. That's how we can do this. So here in this example we find a difference over here. So this statement has 4 legs can be replaced with another representation where X has 4 legs can be represented like this. So instead of having these things in the predicate, we had it inside the parenthesis. So this is how we can represent it. So this gets modified to, let me write it here. So this gets replaced with this. X is a dog. For all x, x is a dog, therefore x has 4 legs. X has 4 legs. Okay, so let's move forward. Fathers are male parents with children. So it's talking about all fathers. X is a male parent. This is how we represent it. Then X has children. So where we found few things here. Since it's talking about all fathers, we will have a universal quantifier, number 1. Number 2, we have to represent X is a father. Then third, X is a male parent. Then 4, X has children. So far we understood these 4 things. That's for all X. If X is a father, then it's for sure that he is a male parent and has children. So for all X, X is a father, then it's for sure that he is a male parent and has children. Okay, so this is how we represented it. We solved it already. Now let's discuss this concept called as universal elimination. Now if we are given with this statement like uh, for all X likes flower, which means that everyone likes flower, and when we are saying everyone likes flower, it means Jonathan also likes flower, because we're talking about every person. Now if we uh, substitute Jonathan for X, this statement becomes Jonathan likes flower. Now there is no point in keeping a universal quantifier here. We cannot keep a universal quantifier here because we are only talking about one person. So when we remove this universal quantifier by replacing it with a constant or an entity like Jonathan, then the universal constant, um, the universal quantifier gets eliminated, and it's called as universal elimination. Now let's try to solve this problem, which is to this day used by philosophers to, for example, get involved into the God's existence discourse. And it was very much popular in the 11th century. There were people like Al-Kindi, Al-Ghazali, and then we have Bonaventure, Saint Bonaventure. They used it when they were discussing with people that belonged to different creeds and beliefs, and they were discussing about the God's existence. Now, if we have a statement which is everything that begins to exist has a cause, the universe began to exist, the universe has a cause. So let's take this statement into consideration and represent it. So if X exists, we will represent it like this. X has a cause, so this is X has a cause, we will represent it with this. Now, but the statement says everything that begins to exist has a cause. So for everything, we will use a universal quantifier, which is this. So we have these 3 things at hand. And we also know that when we have a universal quantifier, then we are going to have an implication along with it. So this statement becomes like this: for all x exists, then it has a cause. Here, universe began to exist. So universe is a constant. So universe is a constant. Universe began to exist, then for sure it has universe has a cause. So this is what we call as a universal elimination. So we have this at hand, which is basically this. This is called as universal elimination, where we eliminate this universal quantifier. So what we saw in the previous example was that we eliminated universal quantifier. Now let's talk about another inference rule, which is existential elimination. It's also called as collimization. As the name itself suggests that we are going to eliminate existential quantifier. Now, what we saw in the previous example of the universal quantifier, any person, if replaced for x, then it was eliminating the universal quantifier. But here, you will not find that kind of similarity because uh, there has to be a particular x that fulfills this condition. Because there could be one person that fulfills this condition, that is, he likes lotus, or there could be two people, there could be three people. Let's have this in our some sort of a knowledge base where we know that John is a person who likes lotus. But there is Mark who likes lotus, and there is Steve who likes lotus. Now, if we try to replace X with uh, someone called as um, Marla likes lotus, then it won't help us in eliminating the existential quantifier because it's not in our knowledge base. We do not have anything that completely endorses this, that Marla is a person that likes lotus. We don't have it in our knowledge base. So uh, here we won't be able to eliminate the existential quantifier. But if someone comes and says that Steve likes lotus, then existential quantifier gets eliminated because it is in our knowledge that Steve is a person who likes lotus. And this kind of constant which helps us in eliminating the existential quantifier is called as a Skolem constant. So this process of existential elimination is called as collimization. Now if we have another example where uh, Jonathan likes lotus. So this is what we discussed already. Now let's shift to this example, which is Jonathan likes X. Let X represent any kind of food, for example. And we have in our knowledge base what is liked by John. So Jonathan uh, likes apple. He likes banana. So these are the things that are stored in our knowledge base. Now, if someone comes and says that Jonathan likes Jonathan likes oranges, then we won't be able to eliminate the existential quantifier because it's not in our knowledge base. However, if someone comes and says that Jonathan likes apple and it is in our knowledge base over here, then it's for sure going to remove the existential quantifier, and apple in this case is a Skolem constant. So that was for existential elimination. Let's move forward. It's called as existential introduction. Now we don't have any knowledge related to thing like someone likes Lotus. Now, if someone comes and says that Mark likes Lotus, and we update this in our knowledge base, we update it in our knowledge base. Mark likes Lotus. So this is the only one statement that we have. Now we are eligible to replace this thing with existential quantifier, because existential quantifier means there exists at least one x such that x likes Lotus. Because now we have a single statement that is basically a testimony, and the testimony goes like that Mark is a person that likes Lotus. Now we updated that in our knowledge base, and since we have this one statement at hand, we can replace it with there exists at least one x such that x likes Lotus. So this is called as existential introduction, which means that this statement could be replaced with a statement that says there exists at least x, one x such that x likes Lotus. Okay, this is called as existential introduction.